make sure to like and subscribe right now. Yes, do it.
On it from MathX, and today we're going to be solving the number 13 from AIME I of 2024. Alright, now this problem can get a little bit tricky as it's a lot of steps and can get like really muddled up because of the high powers. But I assure you there's a quick solution to solving this problem. So without further ado, let's get started. Alright, so let p be the least prime number for which there exists a positive integer n, such that n to the fourth plus 1 is divisible by p squared. Find the least possible integer m, such that n to the fourth plus 1 is divisible by p squared. Alright, now I know what you may be thinking. This looks a little simple, but the thing is, with such a high possible number of answers, and the fact we have no answer choices, it can get a little bit tough because we have nothing to narrow it down necessarily. But I assure you there's a quick way to solving this. So, a quick thing we can do here is that just start to set up equations for the m to the 4 plus 1 divisible by p squared. So, what I would like to do is just start writing some equations. So, m to the 4th is equal to minus 1 mod p squared. That is one thing we can gather from the problem like immediately, since we know it's divisible, that m to the 4th plus 1 has to be divisible by p squared. We can just rearrange that mod kind of equation to get this equation. Now from this equation, we can kind of gather that m pretty much has to be even. So basically, and that's just because of the powers that would work out like that. Like, I assure you, give it a try anytime that you actually have a possible m value for it. So like, let's say p is equal to 3, or actually a better example would be like, I would say 9. But like, we can kind of gather from this that m pretty much has to be positive. So we can start to formulate equations here based on the smallest positive prime number, which would be 2. The smallest prime number in general, to kind of build our equation. Okay, so since we know that p actually has to be the least prime number, we can just plug in the least prime number here in this case, so that would be 2, and we can start to set up equations here. So from this we can gather that p squared would be equal to 16k plus 1. And now, since we know that this is going to be the modulus, since we have to make sure we know that p squared is going to be the least, p squared would be equal to 17, because you're trying to get the least prime number in this case. So, that is a few of the results that we've gotten so far. The next we can do is just set this equal to, so m to the 4th would be equal to 16 mod 17, as we gathered that beforehand, it'd be minus 1 mod p squared. So m to the 4th is equal to 16 mod 17. It's a little tricky to write here, but we'll get that. Mod 17. Alright. Just touch up this equal to. Alright. So we have that so far. Now here where things can get a little bit diluted. So there's a neat trick on how we can get rid of the 16, and it's kind of tough to see the motivation for this. What we want to do is kind of set up a factored form of this. So what we can do is write m squared minus 4 times m squared plus 4 it's going to be a little tough to see it, but it's alright. Yeah, it's a little tough to make that out, but this is m squared minus 4 times m squared plus 4, and this would be equal to 0 mod, I really didn't want to write this with the keyboard cursor, it's a little bit tough, but we got this here. So m squared minus 4 times m squared plus 4 is equal to 0 mod 17. Now next we can kind of conclude what m squared would have to be in this case. Since we're getting the 0 mod 17 and we're always trying to look for the lowest possible answer, this for m, we know that m squared would have to be 13 in this case, because 13 minus 4 times 13 plus 4, so m squared would be equal to 13. So let's just write that again. M squared would be equal to 13 mod 17 actually. So here by here, like little by little, we're kind of reducing powers here, as you notice. Alright, yeah, that's probably the best. Alright, next we can do a similar thing here, and m squared equaling 13 mod 17, we would have to kind of search for all possible of the m squared series. So basically 13 mod 17, that'd be 30, and then after that there'd be a 43, then there'd be a 56, and then after that there would be a 69, and then after that there would be another number. Essentially, we'll have to just find a number for m squared that will be able to suffice here. And if you just look through the possible sequences of 13 mod 17, which I won't be doing right now, as it's a little bit time consuming, but good thing that for AIME problems, you have like 15 minutes to do each problem. We'll find that m is equal to 8 mod 17. Now next, we have to find the smallest one that will be able to suffice for our question in point. So, if you just look through the possible conditions, a few eliminations can be made. So 17, it can be 25. It's just, that's impossible. You'll have to keep going through the sequence. There's like plenty of numbers before it, like 42. Let me just write out a bit of the sequence so you can get started with that. 25, 33, then 41. However, good thing is that a lot of these can be eliminated due to the previous ones. So you'd only have to consider very small amounts, like 33 and 25 can be eliminated. 41, and then there's a few numbers after that. Those were the only ones to be considered, but when you're done with all that, you'd be getting m would be equal to 110. So just like a little bit after our initial one, m equals 110. And that would suffice the conditions of our problem at 8 mod 17. That is 110 mod 17 is equal to 8. So that's the answer to our problem. Now thank you for watching, and I hope you can apply this on the upcoming AIME test in a few months. So good luck, and I hope you have a great day.